Hey, welcome back to Void Drift. I'm Jan, and tonight we're going on a journey. Not to the moon, not to Mars, but much, much further than that. About 190 light years away from where you're sitting right now, there is a planet. A giant, violent, tortured world that has been quietly drifting through space for billions of years. And until very recently, we had no real idea just how extreme its existence actually was. The planet is called HD 80606b, and the story of how we came to understand it is, in my opinion, one of the most fascinating stories in modern astronomy. It starts not with a dramatic discovery in the night sky, but with a slow, patient accumulation of data. Astronomers first detected HD 80606b back in the year 2001. At that point, the tools available to study it were limited. Scientists could confirm it existed, they could estimate its size and mass, and they could roughly map out its orbit. But the details, the really interesting stuff, remained hidden. What they did know was already unusual. HD 80606b is a gas giant, roughly 4 times the mass of Jupiter. Now, Jupiter itself is almost impossible to wrap your head around in terms of scale. It's so massive that more than 1,300 Earths could fit inside it. So when I say HD 80606b is 4 times the mass of Jupiter, I want you to really sit with that for a moment. This is not a small, rocky world like ours. This is an enormous, swirling ball of gas and storms, with no solid surface to stand on, and an atmosphere that stretches thousands of kilometers deep. For years, HD 80606b sat in the astronomical catalogs as an interesting, but not particularly remarkable exoplanet. There are thousands of known exoplanets at this point, planets orbiting stars other than our Sun, and most of them get discovered, cataloged, and then largely forgotten by the general public. But HD 80606b had something that would eventually make it impossible to ignore. It had an orbit unlike almost anything else we had ever seen. Most planets in our solar system travel around the Sun in paths that are nearly circular. The Earth's orbit, for example, is almost perfectly round. We get a little closer to the Sun in January and a little further away in July, but the difference in 0606b is nothing like that. Its orbit is what astronomers call path around its star. For most of its 111-day journey, the planet cruises through the outer regions of its solar system, far from the heat and radiation of its sun-like host star. It's cold out there, relatively calm. If you could somehow stand in the upper atmosphere of this planet during that part of its orbit, you might almost describe it as peaceful. But then comes the turn. Slowly at first, then with increasing speed, HD 80606b begins its plunge inward. Drawn by gravity, it accelerates toward its star on a collision course that it has been repeating for billions of years. And as it gets closer, everything changes. The temperature climbs, the atmosphere reacts, the planet transforms. And now, for the first time in history, we have a telescope powerful enough to watch it happen in real time. NASA's James Webb Space Telescope, the most advanced observatory ever built, has turned its golden mirrors toward HD 80606b. And what it has seen has genuinely shocked the scientists studying it. Tonight, I'm going to walk you through everything. What this planet is, how its orbit works, what Webb actually observed, and why this discovery matters not just for this one strange world, but for our understanding of planets across the entire galaxy. So get comfortable. This is going to be a good one. What is HD 80606b? So now that you know the broad strokes of what we're dealing with, Let's slow down and really get to know this planet. Because the more you understand what HD 80606b actually is, the more remarkable everything that happens to it becomes. Let's start with size. HD 80606b is classified as a gas giant, the same category as Jupiter and Saturn in our own solar system. But it's not just any gas giant. It's roughly 4 times the mass of Jupiter, which already makes it one of the more massive exoplanets we've ever detected. To give you a sense of scale, Jupiter has a diameter of about 140,000 kilometers. Earth's diameter is roughly 12,700 kilometers. So Jupiter is already about 11 times wider than Earth. Now imagine something 4 times more massive than that. HD 80606b is a colossus. A world so large that our entire planet would be little more than a speck compared to it. And yet, despite its enormous size, HD 80606b has no solid surface. There is no ground to stand on, no ocean to sail across, no mountain to climb. The planet is essentially a vast, swirling ocean of gas, hydrogen and helium mostly, with traces of other molecules mixed in. As you descend deeper into its atmosphere, the pressure increases dramatically. The gases gradually compress into denser and denser layers, until eventually, deep in the planet's interior, the hydrogen becomes so compressed that it behaves like a liquid metal. That's a concept that still blows my mind every time I think about it. Liquid metallic hydrogen. A state of matter that doesn't exist anywhere naturally on Earth, but that sits quietly at the core of gas giants across the galaxy. The planet orbits a star that is remarkably similar to our own Sun. HD 80606, that's the name of the star, is a yellow dwarf, about the same size and temperature as the Sun, located roughly 190 light-years away in the constellation Ursa Major. That's the same constellation that contains the Big Dipper, by the way, a part of the sky that most of us in the Northern Hemisphere can find on any clear night. So when you look up at the Big Dipper, somewhere in that general region of sky, 190 light-years away, this entire violent drama is playing out. Right now, as you watch this video, HD 80606b is somewhere along its orbit. Maybe coasting in the cold outer regions. Maybe beginning its fateful plunge toward the star. Maybe right in the middle of being roasted alive. We just can't see it with our naked eyes. But Webb can. One more thing worth knowing about this planet before we move on. HD 80606b belongs to a category of exoplanets called hot Jupiters. These are gas giants that orbit their stars very closely, often much closer than Mercury orbits our Sun. They're some of the most common types of exoplanets we've detected, which is actually a bit surprising because in our own solar system, the gas giants are far from the Sun, not close to it. The existence of hot Jupiters has forced astronomers to completely rethink how planetary systems form and evolve. And HD 80606b, with its extreme orbit and its violent temperature swings, sits right at the heart of that scientific puzzle. The crazy orbit. If there is one thing that makes HD 80606b truly unique, one thing that separates it from the thousands of other exoplanets we've cataloged, it's the orbit. And I want to spend some real time on this, because once you understand the orbit, everything else about this planet starts to make sense. Most planets travel around their stars in paths that are close to circular. Our Earth, for example, stays at a distance of roughly 150 million kilometers from the Sun throughout the year. It gets slightly closer in January, about 147 million kilometers, and slightly further in July, about 152 million kilometers. That's a difference of about 3%, barely noticeable in terms of how much energy the Earth receives from the Sun. Our seasons aren't caused by this slight variation in distance, but by the tilt of Earth's axis. The orbit itself is almost perfectly round. HD 80606b is the opposite of that. Its orbit has what astronomers call a very high eccentricity, a value of about 0.93, where 0 would be a perfect circle and 1 would be a straight line into the star. An eccentricity of 0.93 means the orbit is an extremely elongated ellipse. At its furthest point from the star, HD 80606b is about 850 million kilometers away. To put that in perspective, that's roughly the distance between the Sun and Saturn in our solar system. Cold, dark, distant. At that point in its orbit, the planet receives relatively little energy from its star. Temperatures in the upper atmosphere drop to manageable levels. The planet is, in a sense, resting. But then the orbit curves inward, and as HD 80606b begins its approach toward Periastron, the closest point in its orbit, it accelerates. The laws of orbital mechanics dictate that objects move faster when they're closer to the body they're orbiting. So the planet picks up speed, and speed, and more speed, until at Periastron, it is racing around its star at an extraordinary velocity, just 4.5 million kilometers away. That's about 3% of the distance between Earth and the Sun. Incredibly, terrifyingly close. The full journey from the furthest point of its orbit around the star and back out to the furthest point again takes 111 days. But the time spent close to the star in the intense heat of Periastron is measured not in days, but in hours. It's a brief, violent encounter that the planet has been repeating for billions of years. Like a comet that swings close to the Sun and then disappears back into the darkness, HD 80606b gets roasted, recovers, and then gets roasted again. Over and over, for as long as its star has existed. The roasting begins. Now we get to the part that gave this planet its nickname, the roasting. And I want you to really picture this as I describe it, because the scale of what happens is almost incomprehensible. As HD 80606b begins its final approach toward Periastron, the temperature on its star-facing side starts to climb. Slowly at first, a few degrees, then a few dozen. The upper atmosphere begins to absorb more and more radiation from the increasingly close star. Cloud layers that were stable start to become unstable. Wind patterns that had been consistent for months begin to shift and accelerate. The planet is waking up in the most violent way imaginable. And then comes the peak. At Periastron, with the star blazing just 4.5 million kilometers away, the temperature on the day side of HD 80606b spikes dramatically. We're talking about an increase of over 1,100 degrees Fahrenheit, more than 600 degrees Celsius, in just a matter of hours. To give you a sense of what that means, the average surface temperature on Venus, the hottest planet in our solar system, is about 465 degrees Celsius. HD 80606b's temperature rise alone, not its peak temperature, just the rise, exceeds that in hours. The atmosphere responds to this sudden, extreme heat in ways that are chaotic and fascinating. Chemical compounds that were stable at lower temperatures begin to break apart. Methane molecules get torn to pieces by the intense radiation. New compounds form in their place. Carbon dioxide concentrations shift. Clouds of silicate dust, minerals that on Earth would form rocks, can vaporize and recondense in different layers of the atmosphere. The entire chemistry of the planet's atmosphere is reshuffled, like a deck of cards thrown into the air in just a few hours. And then, Just as suddenly as it arrived, the heat begins to ease. The planet swings past Periastron and begins racing back out toward the cooler regions of its orbit. The temperature starts to drop. The atmosphere, slowly, begins to settle. New cloud layers form. Chemical equilibrium is gradually restored. And by the time the planet reaches the far end of its orbit again, it's almost as if nothing happened. Until next time. The roasting begins. Now we get to the part that gave this planet its nickname, the roasting. And I want you to really picture this as I describe it, because the scale of what happens is almost incomprehensible. As HD 80606b begins its final approach toward Periastron, the temperature on its star-facing side starts to climb. Slowly at first, a few degrees, then a few dozen. The upper atmosphere begins to absorb more and more radiation from the increasingly close star. Cloud layers that were stable start to become unstable. Wind patterns that had been consistent for months begin to shift and accelerate. The planet is waking up in the most violent way imaginable. And then comes the peak. At Periastron, with the star blazing just 4.5 million kilometers away, the temperature on the day side of HD 80606b spikes dramatically. We're talking about an increase of over 1,100 degrees Fahrenheit, more than 600 degrees Celsius, in just a matter of hours. To give you a sense of what that means, the average surface temperature on Venus, the hottest planet in our solar system, is about 465 degrees Celsius. HD 80606b's temperature rise alone, not its peak temperature, just the rise, exceeds that in hours. The atmosphere responds to this sudden, extreme heat in ways that are chaotic and fascinating. Chemical compounds that were stable at lower temperatures begin to break apart. Methane molecules get torn to pieces by the intense radiation. New compounds form in their place. Carbon dioxide concentrations shift. Clouds of silicate dust, minerals that on Earth would form rocks, can vaporize and recondense in different layers of the atmosphere. The entire chemistry of the planet's atmosphere is reshuffled, like a deck of cards thrown into the air in just a few hours. And then, just as suddenly as it arrived, the heat begins to ease. The planet swings past Periastron and begins racing back out toward the cooler regions of its orbit. The temperature starts to drop. The atmosphere, slowly, begins to settle. New cloud layers form. Chemical equilibrium is gradually restored. And by the time the planet reaches the far end of its orbit again, it's almost as if nothing happened. Until next time. The science behind it. Let's take a step back now and think about why any of this matters beyond just being an incredible spectacle. Because the science here goes deep, really deep, and it connects to some of the most fundamental questions in astronomy. One of the biggest mysteries in planetary science is how hot Jupiters end up where they are. In our solar system, the gas giants, Jupiter, Saturn, Uranus, Neptune, formed far from the Sun, in the cold outer regions of the solar system, where ices and gases could accumulate efficiently. The current leading theory is that gas giants form in the cold outer regions of their solar systems, and then, through gravitational interactions with the disk of material around the young star, gradually migrate inward. Some of them end up very close to their stars. These become hot Jupiters. But the details of this migration process are still poorly understood. How fast does it happen? What determines whether a planet ends up extremely close to its star or just moderately close? What happens to the planet's atmosphere during and after this migration? HD 80606b is particularly interesting in this context because its highly eccentric orbit suggests it may still be in the process of migrating. Its orbit hasn't yet been circularized by tidal forces, a process that would eventually turn its wild elliptical path into a more stable circular one. So we might be catching this planet at a transitional moment in its history, a snapshot of a process that our own solar system went through billions of years ago. The chemical changes that Webb is observing in HD 80606b's atmosphere also have profound implications for the search for life elsewhere in the universe. When we look for potentially habitable planets, one of the things we're looking for is stable atmospheric chemistry, conditions that could support liquid water and the chemical reactions that life depends on. HD 80606b is obviously not a candidate for life, but studying how its atmosphere responds to extreme conditions helps us build the models and develop the tools we need to study more promising worlds. Every extreme case teaches us something about the boundaries of what's possible. The planning behind it. I want to take a moment here to talk about something that doesn't get nearly enough attention in science communication. The sheer amount of human effort and ingenuity that goes into making an observation like this possible. Because it's easy to read a headline that says, "Webb observes exoplanet," and not fully appreciate what that actually required. First, the timing. HD 8606b reaches periastron, the crucial moment of its closest approach to its star, once every 111 days. That means the research team had, at most, a handful of opportunities per year to observe it at the right moment. But it's not just about when the planet is at periastron. It's also about when Webb can see it. The telescope has what's called a field of regard, a zone of the sky it can observe at any given time, determined by the need to keep its sun shield properly oriented to protect its sensitive instruments from the sun's heat. This field of regard moves as Earth travels around the sun. So the question wasn't just, when is the planet at periastron? But, when is the planet at periastron and Webb can see it? Finding those overlapping windows took years of careful planning. Then there's the observation itself. Webb's time is extraordinarily valuable. Thousands of scientists around the world submit proposals to use the telescope, and only a fraction of those proposals are approved. The team studying HD 8606b had to make a compelling scientific case for why their observation deserved precious Webb time. They had to specify exactly what they needed: which instruments, which modes, how long, at what times. And once the observation was approved and scheduled, they had to wait, sometimes for months, until the exact moment when everything aligned. When that moment finally came, Webb performed flawlessly. The data it collected has been described by the research team as one of the richest single-target datasets ever gathered for an exoplanet. Years of planning, compressed into hours of observation. That's the reality of modern astronomy. And it's worth pausing to appreciate it. What this means for other planets. We're now getting into the broader implications of this discovery, the part where HD 80606b stops being just a curiosity and starts being a key that unlocks understanding across the entire field of exoplanet science. There are, as of now, over 5,000 confirmed exoplanets. Thousands more are waiting to be confirmed. They come in an extraordinary range of sizes, compositions, temperatures, and orbital configurations. Some are rocky worlds like Earth. Some are ice giants like Neptune. Some are hot Jupiters. Some are so-called super-Earths, planets larger than Earth but smaller than Neptune, with no equivalent in our solar system. Studying all of these different worlds helps us build a comprehensive picture of how planetary systems form, evolve, and potentially give rise to life. HD 80606b contributes to this picture in a very specific way. Because of its extreme orbit, it experiences a wider range of conditions in a single orbital period than most planets experience over millions of years. In just 111 days, it goes from cold and calm to violently roasted and back again. This means that studying HD 80606b is like running a fast-forward experiment on planetary atmospheric physics. The processes that play out over geological timescales on more stable planets happen quickly and observably here. The data from Webb's observation is already being used to refine atmospheric models that apply to a much wider range of exoplanets. When scientists can accurately predict what HD 80606b's atmosphere should look like at different points in its orbit, and then compare those predictions to what Webb actually observed, they can test and improve the fundamental equations that describe how planetary atmospheres work. Those improved models then get applied to every other planet we study. In a very real sense, understanding HD 80606b makes us better at understanding all planets. Looking back at ourselves. And now I want to do something a little different. I want to use what we've learned about HD 80606b to look back at our own world. Because I think one of the most powerful things that space exploration does, and one of the reasons I find it endlessly fascinating, is that it gives us perspective on Earth that we simply can't get any other way. Think about what we've described tonight. A planet with no solid surface, no stable seasons, no consistent chemistry. A world that gets violently transformed every few months by a burst of extreme heat. A place where the atmosphere churns and shifts in ways that would make any kind of long-term stability impossible. A planet that has been through this cycle billions of times with no end in sight. And then think about Earth. Our planet sits in what astronomers call the habitable zone, the range of distances from a star where liquid water can exist on a planet's surface. Our orbit is nearly circular, which means our distance from the Sun barely changes throughout the year. Our atmosphere is remarkably stable, maintained in chemical balance by a complex web of geological and biological processes that have been operating for billions of years. Our planet has liquid oceans, a protective magnetic field, a moon that stabilizes our axial tilt and keeps our seasons predictable. We have plate tectonics that recycle carbon and regulate the long-term climate. None of this is guaranteed. None of this is common. When you look at the range of planetary environments that exist out there, from the frozen darkness of HD 80606b's apastron to the hellish roasting of its periastron, from the crushing pressure of Jupiter to the scorched surface of Venus, Earth starts to look extraordinarily, almost improbably, comfortable. We live on a world that has, so far, managed to maintain the conditions for complex life for billions of years. That is not a small thing. That is something remarkable. The void is just getting started. And so we come to the end of tonight's journey. We started 190 light years away, with a giant planet being cooked alive by its star. We traveled through the science of spectroscopy and orbital mechanics, through years of careful planning and hours of breathtaking observation. We thought about what this one strange world tells us about planets in general, and about our own planet in particular. But here's the thing about space. There is always more. The universe is not running out of mysteries. If anything, every discovery Webb makes seems to open up 10 new questions. The researchers studying HD 80606b have said it themselves. They have only begun to scratch the surface of the data they've collected. There are chemical signatures still to be identified, temperature maps still to be refined, models still to be tested. And HD 80606b is just one of thousands of worlds waiting to be understood in more detail. Webb itself is still in the early stages of its scientific mission. It has years, possibly decades of operation ahead of it. Every year it continues to function is another year of data, another year of discoveries, another year of the universe slowly revealing itself to us. Hot Jupiters, rocky super-Earths, distant galaxies, the earliest moments of the universe. Webb is working on all of it, simultaneously, right now. I find that genuinely exciting. Not just as someone who makes videos about space, but as a human being living on this small, remarkable planet, at a moment in history when we have finally built tools powerful enough to start answering questions that our ancestors could only wonder about. We are the first generation of humans who can actually study the atmospheres of planets orbiting other stars. Think about that for a second. That is an extraordinary privilege. So thank you for spending this time with me tonight on Void Drift. I hope it gave you something interesting to think about as you drift off. The void is vast, and we are just getting started. Sleep well, and I'll see you on the next one.